Hello everyone, welcome to Applied Chemistry Tutorials. Today's topic is Structure of Organic Compounds, Primary Concept. Let's start with the brief introduction. Organic chemistry is the chemistry of organic compounds. The term organic came from the compounds which are obtained from living things, that is animal source and plant sources. Mostly carbon, hydrogen and oxygen are covalently bonded to form organic compounds. Nitrogen, sulfur, phosphorus and halogens are also found in organic compounds. Organic compounds are essentially carbon compounds. Carbon atom has unique property of joining with other carbon atoms through its valencies. This property is called catenation property. Let's see the brief history of the organic chemistry. In 1807, Swedish chemist Jöns Jacob Berzelius first coined the term organic chemistry. Later in 1815, he proposed vital force theory. According to this theory, organic compounds are only formed in living things and cannot be produced in laboratory without vital force. Later in 1828, Frederick Wohler synthesized organic compounds urea, NH2CO, NH2 in laboratory by heating ammonium cyanate NH4CNO. This preparation of urea discarded the vital force theory proposed by Berzelius. Later in 1845, Kolb synthesized acetic acid by combining carbon, hydrogen and oxygen. In 1856, Berthelot synthesized methane gas in laboratory. Synthesis of all these organic compounds proved that no vital force is required to prepare organic compounds and completely discard the vital force theory. So, in conclusion of the definition of organic chemistry, we can say that apart from oxides of carbon, metallic carbonate, bicarbonate, cyanide and carbide, all other carbon compounds which shows catenation property of carbon are called organic compounds and their chemistry as organic chemistry. Now let's see the structure of organic compounds. In 1858, Kekulé proposed the idea that carbon atom has tetravalency with a bond angle of 90 degree. This is the planar structure. And carbon atom can also link with other carbon atoms utilizing single bond, double bond and triple bond, as we can see in ethane, ethylene and acetylene. In 1865, Kekulé explained that carbon atoms can also link with each other using the single bond, double bond to form a ring, and he provided the hexagonal ring structure of benzene for the very first time. But all of these proposed structures are two-dimensional or planar and not useful in explaining the concept of isomers and their differences in physical and chemical properties. So here come the tetrahedral model of carbon. In 1874, Van 't Hoff and Labelle introduced three-dimensional tetrahedron structure of carbon compounds. As you can see here also the tetravalency of carbon are stretched towards the four corner of the tetrahedron and bond angle is 109 degree and 28 minutes. And we have already seen that due to the catenation property of carbon, it can link with adjacent carbon atoms through single bond, double bond and triple bonds. So if we compare the single versus double versus triple bonded carbon atoms, then see in ethane. Here the carbon and carbon are joined via a single bond. Imagine there are like two tetrahedron, individual two tetrahedron as we have already seen in methane. They are joined through a corner so that two carbon atoms are linked through a single bond by sharing each valency of each carbon atom. This way the bond angles remain 109 degree 28 minutes and the structure is also three-dimensional. So they are joined only by the corner. Now in ethylene, where two carbon tetrahedron are joined by through an edge. This way two carbon atoms are linked together by sharing two valencies of each carbon atom and forming double bond. and the bond angle now is stretched to 120 degree, and this gives a planar structure. Now it from three-dimensional it become a planar structure. In acetylene, where carbon-carbon shares a triple bond, now two tetrahedrons are linked via a plane where two carbon atoms are joined through three valencies of each carbon atom. Now the total overall structure is linear and the bond angle now further stretched to 180 degree. So if we compare these three structures together, ethane versus ethylene versus acetylene, it has single bond, double bond versus triple bond. The bond angle, the HCC bond angle here is 109 degree 28 minutes in ethane, 120 degree in ethylene, and further stretched in acetylene as 180 degree. Now if we see the bond length of CH bond length, it is decreased as we are moving from ethane to ethylene to acetylene. It goes from 1.09 angstrom to 1.08 to 1.06 angstrom. Now change in carbon hybridization has effect in change in this bond length. In the upcoming lecture of hybridization, we'll briefly discuss about these changes. Now if we see the CC bond length, as we are moving from single bond to double bond in ethylene, the CC bond length decreases. This is quite obvious because the bond multiplicity increases, so carbon-carbon atoms are getting more closer and the overlap is more tighter, so the bond length decreases as we are going from ethane to ethylene to acetylene. Now if you see the bond energy, quite obvious, as the bond length decreases, the atoms are getting more closer, the bond strength increases, so the bond energy. So the bond energy is increasing from 83 to 145.8 to 199.6 kilocalorie per mole in acetylene. Now if we compare the structure, as we have already seen, in ethane, two carbon tetrahedrons are joined through a corner. So this is three-dimensional structure. Here in ethylene, they are joined via an edge. So this is a planar structure. And in acetylene, they are joined by a plane. So this is a linear structure. So here we conclude the primary concept of the structure of organic compounds. In next lecture, we will discuss about the hybridization. Stay tuned with us. Thank you.